Deep in the shadows, I know it's hard to put one foot in front of the other.
Hi and hello everyone. Today I will be now discussing the subject differential equations, and I will be giving you some backgrounds, concepts and definitions. And before we will proceed to this one, I would like to welcome all the civil engineering students, especially the second year students taking up this subject now in this first semester, and also for other engineering students also who really wanted to learn more about the subject. Okay, so a pleasant day to each and everyone. Okay, so we are now going to proceed with the backgrounds of the subject. And in engineering, mathematical models are developed to aid in the understanding of physical phenomena. And maybe some of you will ask, no, what is this mathematical model or models, no? So these mathematical models often yield an equation that contains some derivatives of an unknown function, and such equation is called the differential equations. Okay, so we can see here that from this mathematical model, we can obtain an equation out of this model. Okay, and this equation contains some derivatives of an unknown function that we can call it later than the differential equations. Okay, so you can understand more fully the meaning of this one as we proceed now in our discussion and in the subject also. And examples of a mathematical model are, first is the free fall of a body or the free falling body, and the second one is the decay of a radioactive substance. Okay, so proceeding with our next slide. So we have here a free falling body, in which we can see it here that the object is a free falling object, in which it is subjected to this gravitational acceleration denoted by this J, and with its mass, and it is at a distance h from the ground. Okay, so we have now this equation actually, m times the second derivative of your h with respect to time is equal now to negative of your mj. Actually, this one, this equation is taken from the Newton's second law of motion, if you can still remember that the force, the total force denoted by this m times j, is just equal now to this mass, of the object times its acceleration, denoted by the second derivative of your h with respect now to time. Okay, so m stands for the mass of the object, and this second derivative of your h with respect to time is the acceleration, and this negative mj, on the right side of the equation is just the total force, So F is just equal now to the mass times acceleration. Okay, so from here we will have now this uh, simplified equation, because our mass will cancel out, from this left side of the equation with the same mass on the right side. So we have now this acceleration, equal now to this negative of your j. And then from here we can take now the integral actually. And we have now this integral sign, no, on the left side, and also you have the integral also on the right side of the equation. So after this, taking the integral of the second derivative of your h with respect to time, take note that when we say with respect to time, no, meaning your t here is the variable, okay? So any other variable uh, excluding t, no, is considered as constant, okay? So our variable here is the time, no, denoted by this t. So taking the integral of this second derivative of h with respect to t is just simply equal to, no, we have here, no, a very simple solution, no, in taking the integral of this second derivative of h with respect to t, so that to give you, no, to give you a good overview on the solution in getting the integral of this acceleration, okay? So we have here, this is just equal now to your dh over dt, no? The integral of this second derivative of h with respect to t is just equal now to the dh over dt, and the integral, no, on this right side of this negative j is just equal now to this, no, integral of negative j dt. So as you can see that we are getting the integral, no, of this with respect now to time or dt. So on the right side, we have to take the integral of this negative j with respect also to time. So that's why we put dt here. Okay? You may wonder nga, why is it nga walay dt din eh, no? But since we are taking the integral and this acceleration is with respect to time or dt, so taking the integral of your negative j with respect to time also, that's why we put dt here. Okay? So I hope it's already understood, no, by you from your previous subject, no, in your integral. And then, as I said, no, that with respect to time, our time is the variable. So here we will consider the gravitational constant j as a constant since t is the variable. Okay, so we extract, no, this negative j outside the integral, so it will become negative j integral of dt. And then after that, taking the integral of your dt is just equal now to t plus your constant. So we denote the first constant here as a small c1. Okay, and then after this, we distribute, no, this negative j to t and this negative j to c1. So negative j to t, so we have negative gt, and then plus here, so we have now this negative j times your c1. Okay, so as you can see, we will assign this capital C sub 1 equal now to this negative j times small c sub 1, no? Since our negative j, the gravitational acceleration, no, is just a constant, so we denote this one as a constant capital C1. So replacing this, so we can say that the integral of your negative j dt is just equal now to negative jt plus then your capital C sub 1. Okay? So this would be it, no, as to the integral of this second derivative of h with respect to t, and this second, this integral of your negative j with respect also to time or dt. So we can have now this equivalent here, no, dh over dt, which is the integral of this acceleration equal to dh over dt, And this integral of negative j with respect to time, since we are talking about this with respect to time t, so we have here the equivalent, no, of this integral of negative j with respect to time, or dt. So we have here negative gt here plus your c sub 1. Okay, so after that we are taking the integral again, no, because still it is not yet simplified, no. It is still as a function of your this is acceleration, so this one would be now its velocity, no, dh over dt. So we take an integral again so that we can simplify this one into a single variable h, no, in terms of height. Okay, so taking the integral, so again we will put integral sign, no, here and also here. Okay, so simplifying, so we have now this brief solution, no, on how to get the integral of your dh over dt, which is equal now to h, and then the integral of this negative gt plus c1 with respect also to your time dt. So as you can see it here, integral of negative gt plus c1 here in terms, no, with respect to dt. Okay, so here we can actually simplify this one, no, individually. So you distribute the integral to each term. So this would be integral of negative gt dt, no, with respect to time, then plus you distribute the integral here, integral of c1 dt. So that would be integral of c1 dt. Okay. So after this, we are going to extract, no, the constant, no, out on this integral sign. So dt. So our variable is t. So therefore, the only constant for the first term here is negative j. So that's why we extract out the negative j outside the integral. So what remained is this t dt. Okay, plus the only constant is c1. So extract out c1 integral of dt. So proceeding, we have now this taking now the integral of t dt, no. So from your integral calculus, no, our n here is a 1, no. So the integral of t dt is just t to the n. Example is t to the n plus 1 over n plus 1. So here our n is 1. So n plus 1 is t2 over n plus 1 is 2. Okay, so 1 plus 1 t squared over 2 plus your small c2. Okay, so we assign small c2 here because based on our first, no, assignment is we only assign small c1. So basically we cannot assign again c1 here. So what's next for the c1 is the small c2. So that's why we are using the constant small c2. Okay, plus this integral of dt is just t plus we assign c3 because we already have c1 and c2. So this is small c3. And then simplifying, no, we distribute this negative j to its term here. So negative j t squared over 2 here, and then negative and positive. So this is negative jc2. Okay, and we have here plus we distribute here c1t. So this is plus c1t, no, capital C sub 1t, and distribute capital C sub 1t to small c3. So plus capital C sub 1 times small c sub 3. Okay, so take note that this c is just simply constant. No, c1 is constant and c3 is also constant. So again, we are going to rearrange, no, to separate, uh, to combine the constants, and then to separate also the terms having variables, no. So in this case, our variable is t, since we are with respect to time, no, dt. So we have here negative j t squared over 2 plus the C sub 1t here, and then rearrange, no? Minus GC2, since this is constant, plus this constant again, C sub 1, C sub 3. Okay? So by this, we can assign, no? We can assign capital C sub 2. Why capital C sub 2? Because we already did assign, no? Capital C sub 1. So that's why we are using capital C sub 2. Okay? So this capital C sub 2 is just a constant assigned to a constant also here, no? To simplify it, no? Because we have a lot of constant, no? Small c sub 2, small c sub 3, and capital C sub 1. So to simplify this one, so we will assign capital C sub 2 equal now to negative j c sub 2 plus c sub 1 c sub 3. Okay? So by this, we can have it now as negative jt squared over 2 plus your capital C sub 1t, and then the assignment here is C2 plus this capital C sub 2. So as you can see, this would be now its equivalent, no? Here. Okay? So we have now, since our integral of dh over dt is equals to h, so this one is h, okay? In which you can also put h as a function of time because it is with respect now to time, or dt, okay? Which is equal now to this obtained values here, no? The negative jt squared over 2 plus your c sub 1t, no? Plus c sub 2 here, okay? So I just show the step-by-step solution here so that this will serve as your guide, no? On how to get these values here, no? This formula. This is actually a formula, no? In which we can get now the value of your h, no? As a function of your time t here, okay? So if you have a time value, so you can actually get your h, okay? So I think it's already very clear, no, to all of you that this is just an overview, no? This is actually an overview for this free-falling body that involves differential equations. That from here, no, this differential equations, which is the second law, Newton's second law of motion, so we can arrive, no, with this formula in getting the value of your h, no, with respect to time or as a function of time here. So now we are going to proceed now with the second one, the radioactive decay, and from here we will deal now with this differential equation. Derivative of your a with respect to time is equal now to negative k times your a, where your value of k must be greater than 0. So here the a now is the amount of the radioactive substance, no, for this case, no, this second mathematical model. And then if we are going to simplify this one, so we have now this, you just cross multiply, no, so we can have this dA here, dA over a, or 1 over a dA is equal now to this negative k times your dt. Okay, so here from this equation we take the integral. Okay, so we put an integral on the left side of the equation and also on the right side, and then solving for the integral, so I can give you a solution on this one for this integral of 1 over a dA, and also for this integral on the right side of this negative k dt. So we will discuss first this integral of 1 over a dA, in which this is just equal now to the integral of dA over a, no? So we are having this form, no, because we knew, no, from your integral calculus that we have this integral of du over u is just equal now to this ln u plus c, where in this case our u is our capital A. So by simply using this, no, we have now this integral of d over a is equal now to ln of your a plus your small c sub 1, no, which is your first constant. Okay, this is our first constant because we are dealing first, no, this first integral on the left side of your equation, and then assigning capital C sub 1 is equal now to this small c sub 1, so we can obtain, no, this integral of this d over a is equal now to ln of your a plus capital C sub 1, no? So as you can see it here, no, this would be now our integral of this 1 over a dA, the ln of a plus c1. So how about this second integral, no, of this negative k dt? So we have also here, no, step-by-step solution, no, on how to get the integral of this. So from here, with respect to time, no, dt, so the t here is variable, so therefore we can say that our k is just a constant. So we will extract, no, this constant k outside integral. So that's what we did here, no, negative k integral of dt. And then after that, we get the integral of this dt, which is t plus c sub 2. So small c sub 2 because we already have this constant small c sub 1. And then we distribute this negative k to t and to c2, so we can have negative kt and then negative k c sub 2. And then we will just assign, no, since k is constant and c2 is constant, so we will let, no, capital C sub 2 is equal now to this negative k small c sub 2. So we can have now this simplified, no, value of your integral of your negative k dt is equal now to negative kt plus your constant capital C sub 2. Okay, so we can actually substitute the value, this one here and this one also on the right side of the equation. Okay, so we have now this ln a plus capital C sub 1 is equal now to this negative kt plus capital C sub 2. So you may wonder why is it that it is enclosed in parentheses. It is just equal, no, or equivalent, no? So ln a is just equivalent to ln of this enclosed a, no, in parentheses. Okay, so again we are going to simplify this again, no. So how we can get the value of your a, no, since we are after on the value of the substance, no, this radioactive substance a. So actually we can rearrange this one, no, for solving for a. So we can maybe we can combine this c sub 1 to the right side, no, and then we isolate the ln a since we are after on the value of our a, no, this one. Okay, so I have now this simple illustration, no, showing how we did this solution for this, no, for getting the value of a. So we have here ln a plus capital C sub 1 equal now to this negative kt plus capital C sub 2. So we rearrange, no. We have isolating the ln a since we are only after to this value of a, no? And this is equal now to negative kt plus capital C sub 2, and this would be negative C sub 1. And then we exponentiate, no, exponentiating this 2, the left side and also on the right side. So we have exponentiate ln a, and this right side also in exponentiating, no, this one. So we have e raised to the ln a is equal now to this e raised now to this negative kt plus c2 minus c1 here. Okay, and then after that is we will take note also that we have now this e raised to the ln x is just equal to x. Okay, so this is a special property, no, for exponentiation, and our e raised to the negative kt plus c2 minus c1 is just equal now to the product, no, of this e raised to the power of negative kt times e raised to the power of c2 minus c1. Okay, and then as you can still remember that if we will raise, no, e raised to the power of constant is just simply equals to constant. Okay, e raised to the C2 minus C1. C2 and C1 is constant. Okay, so e raised to the constant is just simply a constant, and we will assign capital C for this. No, so we can say that our e raised to the ln a equal now to e raised to the negative kt plus C2 minus C1 is just simply equal now to e to the ln a is equal to a, no? Since we have now this special property, okay? E to the ln x is equal to x, and our x here is a, no? So that's why this is a. Equal now to this one, e raised to the negative kt here, okay? Times e raised now to this, e raised to the C2 minus C1. But since our e raised to the C2 minus C1 is constant, we will assign capital C. So this would be then equal now to a raised to the negative kt times c. Or simply, your a is just equal now to c times e raised to the power of negative kt. So therefore, we can say that your a, no, your a is just a function of t, since k is the constant, proportionality constant rather, no? And since a is a function of t, so a is just equal now to a of t is equal also to this c times a raised to the power of negative kt. So that's why we have now this answer, no, for this radioactive decay. Okay, so a is equal now to a as a function of time, since this is a function of time with respect to t. Okay, is equal now to this c times e raised now to the power of negative kt. Okay, so proceeding now with this definitions, annotations, no? Since that is just purely an overview, no, of the background or introduction of this differential equation. So more or less, you're now familiar, no, a little bit familiar that this would be now our inclination, no, in this subject, differential equations. So we will come now to the definitions, annotations, no. So we have here a differential equation, simply having this d e is one that contains at least one derivative. Okay, so if it involves a derivative, so you can say that it is a differential equation. We have also here the order of a dE or differential equation is the same as the power or exponent to which the derivative of the highest order in the equation is raised. Okay, and a dE may be ordinary or partial as to the type of derivatives or differentials appearing in the equation. So later, no, in our later slides, I can give you an overview of what this ordinary and partial derivative, no, are all about, no. So we have here the solution to a dE is the relation involving only the variables and arbitrary constants, free of any derivatives or differentials, and consistent with or satisfying the given differential equation. So when you speak about the solution, no, it could be a general solution or a particular solution. So you can say that it is free, no, from any derivatives or differentials. So you can call that one as a solution. Okay, so proceeding, the most general solution of a differential equation of the nth order contains n arbitrary constants. So kindly take note on this, because later on, no, in our succeeding topics, you can fully understand this statement, no, especially if you are involving with the nth order, no, of the differential equation. If particular values are assigned to these arbitrary constants, the solution is called the particular solution. And arbitrary constants may be obtained from known boundary conditions. Okay. So this is just an overview, actually, no. So do not be confused, no, because I will just giving you the overview of the subject. And we have also a first order differential equation is written in either of the following forms, no. So you can write it as an implicit derivative, by having this f as a function of your dy over dx, x and y is equal to 0, or you can have this implicit differential having this form m as a function of your x and y dx plus n as a function of your x and y dy is equal to 0. And you could also have this explicit derivative, no, where you have this dy over dx is equal now to the function of your x and y. Okay. Again, we also have this linear differential equation, and this can be written in this form. No? As you can see, this is the general, no, form of this linear differential equation. And then, as you can notice, no, your a sub n as a function of x, and then times this n derivative of your y with respect to x. And then the second term is a subscript n minus 1 of x. And then the derivative is d, and n raised to the n minus 1 over the x n minus 1. No? So as you can see it here, no, you can observe that if you have this n term, the next one is n minus 1, and also the derivative is n into n minus 1. So until it reaches, no, this is sub 1, so your dy over dx is 1, okay? Until such that you have now this e sub 0, okay? And you no longer have the derivative but as a function of x only, equal now to this f as a function of x, okay? So we have here where a sub n as a function of x, and this a sub n as a function of x until a sub o as a function of x, and f as a function of x depend on the independent variable x. Take note, independent variable x, okay? And we have here, if an ordinary differential equation is not linear, so if it does not satisfy, no, this given general formula, so it is called nonlinear. So to begin our study of differential equations, we need some common terminology, and if an equation involves the derivative of one variable with respect to another, then the former is called a dependent variable, and the latter an independent variable. Okay, so we have an example, no, of this dependent and independent variable. So from this given differential equation, our t, no, dt here is the independent variable, and our x is the dependent variable, and we refer to this a and this k as coefficients in the sample equation. And additionally, we have a differential equation involving only ordinary derivatives with respect to a single independent variable is called an ordinary differential equation. Okay, so it involves ordinary derivatives, so therefore it is an ordinary differential equation. And a differential equation involving partial derivatives with respect to more than one independent variable is a partial differential equation. Take note, involving partial derivatives. So there's a hint already, no? If it involves ordinary derivatives, an ordinary differential equation. But if it involves partial derivatives, so it's a partial differential equation. And we have now an example for this ordinary differential equation. As you can see, no, an ordinary derivatives, and for the partial differential equation, no, having this sign, no, of this partial derivative. Okay, so I think that would be it, no, for this video, no, for this meeting. And for our next video or videos, we have 1.1 and 1.2. We will discuss sample problems, no, involving dependent and independent variables, the order of the differential equation, classification of the differential equation, and the linear and nonlinear differential equations. Okay, so these are also my references, no? So you can access them, no? And again, thank you very much, no, for watching, no, of this lecture video, and I hope that I impart something new, no, and I impart knowledge, no, sa inyo mga students. So once again, thank you for your time, no, in watching this video of mine, and I hope that in my next video, video 1.1 and 1.2, you can still see them and watch them, and I hope also that you can learn something out of those video and also from this video. So again, have a pleasant day, and thank you, and keep safe, everyone.